to collect people before I go live. And we're getting people in chat. Hey, Eaton, Jack, Yatin, Sam, Sergio. Hey, Sergio, good to see you again. Is Ultima Thule flat? Like okay, so Jack, right off the bat with the questions, this is exactly what this show is for, where it's just super casual. Just me sitting in my very, very dark office with you guys, with all my best friends, talking about science. Can you guys hear the music, or did the music shut off? What happened to the music? Because I had some cool background tunes. The music is still going. Oh, I think I shut it off. Is that it? There's the music. There's supposed to be some groovy background music to go with us tonight. And it's all free and clear. Let me know if the music's too loud, because I actually can't hear it. So I actually have no idea what the music is like, is if it's any good or whatever. Hey, Craig. Hey, Timothy. K. Spence. I know, it's like being back on the boat. Motorcycle Zero Show. Okay, so I'll just go ahead and jump right into questions. Is Ultima Thule flat like the Earth? I get it. That's a joke, right? That's a joke. Here's a picture of Ultima Thule. There it is. That is very much not flat. I mean, the picture is flat. This is just a two-dimensional image, but of a three-dimensional object. In fact, NASA provided, the New Horizons team, they did stereoscopic images. So you can put on those dorky, like red-green or blue-green, red-blue, one of the colors, red-blue glasses, and then you can see like the little divots and stuff. It's not that impressive. I'm sorry, New Horizons. I mean, it looks cool, and you think like Ultima Thule is gonna like jump out like this. It's small. I know it was a joke, Jack, but I want to play along with the jokes. I am in incognito mode. So here's why my browser is in incognito mode. Because I don't want you seeing my bookmarks. I don't want you seeing my favorites. I don't want you seeing my history. If I have to go Google something, you don't want to know my searches. You don't know what I've been looking up for the past hour. Nobody wants to go there. Nobody wants it. I keep hearing about upper field theory. What is it? I've actually never, ever heard of upper field theory. Sorry, I actually don't know. I'll look it up. I'm guessing if I haven't heard of it. Do you mean mean field theory? Mean field theory is great. Mean field theory is very, very useful. Look at all that useful math. Oh man, we've got Hamiltonians. We've got products. Mean field theory is great. Upper field theory, I'm not going to go with. What's the far side of the moon like? The ridiculous thing about the moon is how different the far side is. And Chang'e, the Chinese lander, just went there. I mean, look at that. Oh, that's the tiniest image ever. Is this useful? No, it's not. This is good. Oh, unified field theory. That's better. Yes. I'll talk about unified field theory. Check this out. On the left here. Okay, I'll scroll so you guys can see it. I can't scroll so you guys can see it. I'll work on it. See, this is my first time doing a show like this. Look at that. Oh, the chat's in the way. Okay, well, there's the far side of the moon right there. Totally different than the near side. The near side has all these lava flows and the mare, and it looks like it was active, like interesting things happened. The far side of the moon is just Crater Town. It's just Crater City nonstop. Totally different structure and surface composition. It's It's crazy. Will Chang'e 4 bring back a sample? No, it's not a sample return mission. It will rove around, so it will scoot along the surface. It might poke and prod. We know some things about Chang'e, but the Chinese aren't saying a lot. Like, we weren't even exactly sure when it would land. We just got the news like, hey, surprise, you Americans are all celebrating your flyby of Ultima Thule. We also happen to land on the far side of the moon, just saying. And it was a surprise for everyone. Yeah, I know, the dual monitors. Okay, I'll get there. Hey, contribute to my Patreon so I guys have. This is all off my laptop, folks. This is all off my laptop. I've got my microphone. I've got one of these little ring lights. Thought you guys might like it. You see that? That's handy. That's my lighting setup today because I thought if we're going to be chill, if we're going to be low key, I didn't want to get the full rig out with my camera, with all the studio lights and the backsplash and what I normally do. I wanted to be, it's just us. It's just us. Face, yeah, Cosmos Kramer. They're looking for the American flag. They're on the wrong side. They got mixed up. They got the wrong directions. A giant liquid telescope on the far side of the moon. So having a telescope on the far side of the moon would be great, actually, because there's no air and there's ground. You know, if you want a telescope, it's nice to like anchor it in dirt so it doesn't move all over the place, and so you can build something really, really big. So might there be an observatory on the far side of the moon someday? Maybe. I mean, hundreds of years from now, but we might get there. Cozy place, thank you. Are you talking about my office or the far side of the moon? Both equally dark. Except, okay, the far side of the moon is not the dark side of the moon. It does get illuminated by sunlight. Every once in a while, I still slip and call it the dark side of the moon because it sounds cool. If something sounds cool, it needs to be said. Face Gallon is asking, is dark energy negative pressure forcing expansion? I hate the term negative pressure. Whatever physicist decided that, like, and this is probably in the 90s, like, okay, folks, we're going to explain, every once in a while in general relativity, you can get things flipped around. We're going to call things negative pressure, and that's just going to make sense. And everyone will know what we're talking about. You just walk up to someone and say, hey, dark energy is negative pressure forcing the expansion of the universe. That makes no sense. Dark energy, negative pressure is one of the worst terms in physics. And there are a lot of really, really bad terms. I could go on for days about all the bad terms. But negative pressure is definitely up there because negative pressure, I mean, think about what pressure is. Pressure is if you have a balloon filled with air, and you heat up the air, there's a lot of pressure and it'll make the balloon expand. That is pressure. So what is negative pressure? Well, that's pulling in. If you take a rubber band and you stretch the rubber band, it stretches, you can feel the rubber band pulling back on your hands, right? That's tension. Tension is negative pressure. Negative pressure is just a fancy, overcomplicated, useless way of saying tension. And so what makes it even worse is that you're saying, okay, if dark energy has negative pressure, if dark energy has tension, how does that make the expansion of the universe accelerate? Like, if there's tension, shouldn't that pull rather than push? And what the lamest thing in the world is, it's all in the math. It's all in the math of general relativity. It turns out, for no reason that you would absolutely expect ever, that if you have something, a substance with a lot of tension in it, it actually causes anti-gravity. Now, you don't notice this in like a rubber band. If you have a rubber band and you're pulling on it, there's tension from the rubber band, but then there's also the mass of the rubber band itself. And the mass of the rubber band itself has normal gravity. The tension has anti-gravity, but that tension is super, super small compared to the mass, so it doesn't matter. But when you go up to something like the whole entire universe, and you fill it with something like dark energy, which has very, very little mass, very little energy density. It's very, very tiny, but it has enormous amount of tension. then the equations of general relativity flip around and you end up with anti-gravity. So anti-gravity is allowed. Anti-gravity is a thing in our universe. You just need an enormous amount of tension in order to trigger it. And that's what appears to be happening all across the universe. Yes, it's just not the best term. I don't like it. Breaking news, Paul's office is on the dark side of the moon. That's it. I am sitting in pure vacuum right now in one of the craters. I forget the name of the crater. I just got here like a couple months ago and I've been setting up. I'm still moving in. Everything's in boxes. You know how it is for the first few weeks in a new place. Right. Arambe's ghost, all that tension triggered the universe's fight or flight response. That's actually a really fun metaphor. I really, really like that. I might use that. Like, with all the tension in the universe, it just had to go. It just had to get out. Does mass increase with speed? It does. It does. Mass does increase with speed, which... This is a weird thing, isn't it? This is a weird thing. That literally, when you start running, even when I start running, and I can barely run. When I start running, I gain mass, which is ironic because you might run to lose mass. Turns out in that when you're actually moving, you have more mass. And the reason for this is that mass is energy. Energy is mass. Mass is energy. They are the exact same thing. So the more energy you have, the more mass you have. Full stop. Full stop. So a hot cup of coffee has more mass than a cold cup of coffee. Straight up. I mean, it's a tiny, tiny amount, but so don't even bother trying to measure it, but it's there. A hot cup of coffee has more mass, weighs more than a cold cup of coffee. If I take that cup of coffee and I throw it, it now has kinetic energy because it's moving. Energy is mass. A moving cup of coffee has more mass than a stationary cup of coffee. A running Paul has more mass, ironically, than a stationary Paul. And so moving objects have more mass. Kevin Ayers, welcome aboard. It's never too late because I'll be here for a while, folks. Does Ultima Thule have a stable axis of rotation? I think it is. It is rotating on its axis, that dumbbell thing. As far as we can tell, it's not tumbling or anything like that. It's just spinning on its axis. If there is no dark matter, is Einstein wrong? We would love, and I talked about this in the latest Space Radio last week, about moving past Einstein. And one of the complications we've run into, or one of the things we've run into, is dark matter, right? We have this set of observations where the universe isn't behaving according to expectations, where observations aren't agreeing with each other. And that happens all the time. Like, this is life. And especially when it comes to gravity, you can look at all sorts of different examples of like, wow, this thing isn't moving like we expected it to. And when something isn't moving like you expected it to, it could have a bunch of reasons. One reason could be maybe your theory of gravity is wrong, your understanding of motion is off, or maybe there's other stuff out there that you didn't know existed before. Maybe there's just new stuff. And both examples have been revealed in the past. So when we looked at the motions of the outer planets, like Uranus, it didn't follow expectations. It wasn't agreeing with our predictions. And so we had to add a new ingredient to our universe. We called it Neptune, and then we found Neptune. But then the same thing happened on the inside of the solar system where Mercury wasn't behaving properly. And we go look at Mercury, and for a while there was proposed a new planet within the orbit of Mercury called Vulcan. Looked for Vulcan, couldn't find it, couldn't explain the motion, the orbit of Mercury. And we needed a new theory of gravity. We needed general relativity to explain the orbit of Mercury. So when we look at something like the motions of stars inside of galaxies, and the fact that stars are going around way, 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 way too fast, either there's new stuff in the universe or a theory of gravity is wrong. But every time we try to cook up a new theory of gravity, it doesn't work. It just doesn't work. It fails. So we get stuck. Einstein passes every single test. We have no compelling theory of gravity past Einstein. And the dark matter explanation works. It just fits all the data. Now, we haven't actually seen it yet, which is getting a little bit worrying, but we're working on that. Give us a few more years before we start to get really, really nervous. But there it is. Chemistry Guy, could you please do some more crossover episodes with Isaac Arthur? So here's the thing about Isaac Arthur. A great guy, amazing channel, a huge success, came out of nowhere, I think 3 years ago. Started with absolutely 0 subscribers and now is at 300,000 or something ridiculous. Isaac Arthur does a lot of speculative fiction where he takes some idea and some concept, from science fiction or some super highly theoretical physics, just some ideas, and he expounds upon them, which is fine. I've absolutely no problem with what Isaac Arthur is doing on his channel. But that's not what I do. That's not what I talk about. I don't talk about speculative fiction. I don't talk about science fiction. I, of course, work with science fiction authors and movie makers and TV show people. I love collaborating with creative people like dancers, like authors, screenwriters, producers, the whole deal, to help craft their worlds. And that's actually really, really fun and fulfilling. But it's not something that I present personally to the public. I don't go up on stage and talk about, futuristic ideas for terraforming Mars or something. That's just not what I do. So I have no problems with Isaac Arthur or his channel, but and I did a collab with him before. I think it was the Compendium of Doom of various ways that the universe will end or the life might end. And that was really, really fun. If there's another topic that we could do together that fits, that makes sense for what I do and what I talk about on my channel, I'd be happy to. But we just haven't connected ever since then. We've moved on. Let's scroll down. Yeah, and John Michael Gaudier, I've done collabs with him. Super fun guy, John Michael Gaudier. He's actually leading one of our Astro Tours, or joining with us an Astro Tour to Joshua Tree National Park this June. So if you want to hang out with him live, you can. He's a really fun guy to chat with. Oh, Timothy, can you explain what you mean by... I'll ask, Iten, do I have a telescope? Okay, so technically I personally do not own a telescope, but my company Astro Tours does, and the telescope happens to be in my basement, and I maybe take it out every once in a while. I don't know. I have an 8-inch Celestron. It's a really, really nice scope, super simple to set up. The folks over at Oceanside Photo and Telescope helped us out with that one, and we drag that telescope all around the world, which is a hilarious enterprise every single time, because it has a giant case, a rolling case just for the scope and the mount, and then the tripod has its own case, so I'm always wheeling through airports with these 2 giant bags, and that's always just generally amusing, and lots of skeptical looks from customs officers. So it's not technically my telescope, but it happens to be within my possession, and I happen to use it all the time. So I don't know if that counts. Hey, Nitish, welcome to the channel. And we've got a question here from Timothy. Can you explain what you mean by observable universe? How can it be 46 billion light years in radius when we can't see the light from that far away because it hasn't gotten here yet? So yeah, this is always a confusing concept. So wonderful question. Our universe is 13.77 billion years old, right? And so you might think that with the speed of light being the speed of light and the age of the universe being the age of the universe, that over the course of 13.77 billion years, our observable universe, the limit of what we can see in our universe, should be 26 billion light years across, or 27 billion light years across, a radius of 13.77 billion light years. But it's not. It's way bigger. Our universe has a radius of 46 billion light years, not 13.77 billion light years. And the reason for that is that our universe expands faster than light. And that's not a problem. So what we're seeing when we see a distant galaxy, and that light has just now reached our telescopes, and what we're doing is we're reconstructing the position of that galaxy where it is now. Not when it emitted its light, but where it is now. So imagine two galaxies here. They're next to each other. Our universe is expanding. They're moving apart. This one sends a postcard, like boop. And then that postcard takes time to travel to us over here. But in the meantime, so this one, boop, spits out the postcard. That postcard starts traveling. This is where I need a third hand to really give this metaphor justice. But in that time, while that postcard is being sent, our universe has expanded. So now the galaxies are over here. So now we receive the postcard over here. We say, okay, and we can do some math. And we can figure out that this galaxy is way over here. But when we receive that bit of light, and in the intervening time, our universe has expanded faster than light. And so that galaxy can be very, very far away. Andrew Cox, that's taking space expansion into the estimate, right? Yes, that is exactly right. So this is what's called a model-dependent answer. So you actually have to put in the ingredients of the universe. You need to know a little bit about the universe. You need to know that our universe is expanding. You need to know what it's made of. You need to know about dark matter and dark energy. You need to have some estimates. You need Hubble's constant floating around somewhere. You need some model, and then you put it in. You say, this is the redshift of the light that I received. You put it into some formulas. You do some number crunching. There's even calculators available online. Just Google search. I can do it for you. So I can call. What can we say? Ned Wright cosmological calculator. Please, no one judge my typing skills. So you can see over here on the left, like these are cosmological parameters, like the current value of Hubble's constant, the amount of matter in the universe, a given redshift, the amount of dark energy. And you put in like, okay, I see something, and let's say it has a redshift value of 1.7, and we live in a flat universe. Gives you the age, current age of the universe here, 13.7. This isn't current cosmology here in this little calculator, so that's a little bit off. The age at redshift 1.7, our universe was only 3.8 billion years old, and you can see the distance out, the volume, everything. There it is, 43 billion light years away, a redshift 1.7. So this is a calculator. This comes out of a model. It comes out of a model of the expansion history of the universe. Andrew Cox, do I do any software development? Yeah, I've done. So all physicists and astronomers are basically amateur software developers. So I've written a lot of, wrong URL. I've written a lot of codes in my day. I've written a lot of stuff, and probably the biggest thing I wrote is this thing called the Public Cosmic Void Catalog. This is a few years out of date because I haven't kept it up to date because I've moved on to other things. But this is something I wrote of studying the large-scale structure of the universe. So this is the universe at the very, very biggest scales. And this is looking at nothing at all. The giant voids that sit between the galaxies. Together with some collaborators, Ben Wandel, Guillaume Laveau, David Weinberg, Nico Hamas, Alice Pisani, a few others, we developed this big software package where you could put in either a simulation of the structure of the universe or actual raw observations. It would chew through it, and we developed a special algorithm for finding voids using watershed techniques. So the exact same algorithm that topological researchers use to find where rivers and lakes and streams are going to flow to. It's the exact same math. We would use it to find the cosmic voids. And then we made these catalogs publicly available, and we also made our code publicly available. So I think it's still, oh, there it is. It's over on Bitbucket. It's a giant Python package with a bunch of C backends, and I'm actually quite proud of this. This package that we made, because we wrote a bunch of papers. We wrote, I don't know, like a dozen papers about cosmic voids over the years. And this software package allows you to recreate all of our papers. So every single plot, every single table, every single bit of analysis that went into our papers, you can generate with this freely open source code. So you can download it, you can grab our exact same data that we use, you can run through the exact same analysis, you can pick us apart and find flaws. And people did. People found mistakes that we made, both in the code and the analysis, and that helped us write other papers. See, I can give you an example of one of the papers we wrote using this software package. So I have to vanity search myself. These are my papers, by the way. My beautiful, beautiful papers. Did I write that one? What's a good one? Oh, blank papers. There's a good one. Aha. This was a summary paper I wrote when we released the full package. So this shows you some pretty pictures. Large scale structure of the universe. That's what a void typically looks like. You can't see it because the chat's in the way. Should I just why didn't I think of this? I can just disappear the chat. So all these kinds of plots, which make absolutely no sense unless we dig into some pretty hefty statistics. All these plots were generated with this open source package. And you can see that's a very Python looking plot, if you know what Python plots look like. So all this stuff. Oh, 2 plots? I thought I had more. Oh, because this was the conference presentation, not the, never mind. So you get the idea. So I have done software development. I don't do too much software development nowadays, just because I'm doing live streams, I guess. Chemistry guy, I was wondering if you could help with a bit of my dilemma. I'm a teen who loves both astrophysics and organometallic chemistry, hence your name. You're looking at incomes. Virtually, okay. Whew. Okay. I'll tell you. If you're looking at STEM careers, if you're looking in sciences, either astronomy or chemistry or whatever, the absolute worst thing you can do pay-wise is pursue a Ph.D. and enter academia. Because for a couple reasons. One, when you're in grad school, if you're in STEM, you'll typically get paid for grad school, so that's not so big a problem. But you're not going to get paid a lot, and you're delaying your career by 6 years. So when all your friends who just have bachelor's degree go out, they get entry-level jobs, and then 6 years later, they're in management or senior developer or head technician or whatever. You're still just in school. So it delays your career by at least half a decade. And then if you continue in academia, professorships do relatively pay well. I mean, whether it's a research institution or teaching university, typical STEM research university, you're talking, 70 to 100,000 a year. But that's after years and years and years of doing relatively low paying postdocs. So you're not looking at that kind of salary until you're in your mid to late 30s at the earliest. And it's nice, but again, it's delayed. So all your friends who went right into industry have been hitting that same salary benchmark, but just like 5 years behind you. So they've been investing in retirement for longer. They've been able to buy a house and settle in, before you have. So when it comes to salaries, and that's an important consideration. That's an important consideration is, your salary range, your expected salary, how many times you'll have to move. If you're in pure academia, you're going to have to hop around from job to job for years before you land a tenure track position. There's relatively few jobs in academia. Any STEM field has very, very few professorships open. So you're going to be hopping around. You won't be able to buy a house. You won't be able to settle in. Raising a family is an incredible challenge. And whether it's in chemistry or astronomy or something else, it's going to be a challenge to stay in academia. It really is. And I feel like this is a not very well talked about thing about how challenging, how high the expectations are in academia, and how little the training you receive actually prepares you for life outside of academia. Because the assumption is that if you're in grad school, well, we're going to train you to be an independent researcher and a professor someday, except there's barely any jobs as independent researchers and professors. So 9 times out of 10 at worst, or at best, at least 9 times out of 10, you're not going to be in a professorship position. You're not going to be an independent researcher, simply because there aren't enough jobs. And for sure, the skills you learn and the skills you develop as you're pursuing your Ph.D. and as you're going into postdoctoral appointments totally transfer. You've got some amazing skill sets that any employer would be eager to get you on their team. No doubt about it. But you're not going to receive, how do you write a resume? How do you do a job interview? How do you work in a corporate environment? How's it different than an academic environment? That's going to bite you, and that you're going to have to learn that when you actually jump into the job. Don't expect to get that from your professors or your peers. Yeah, Andrew Cox, I always hated how research universities force their professors to write 10 papers at minimum just to keep their job and minimum salary. Distracts from their teaching and research. So different universities have different criteria for maintaining your professorship. Really, the big hurdle is tenure. Once you start as an assistant professor, you've got 5 years. And it depends on if it's a teaching university or research university, if it's high level or low level, blah, blah, blah. A typical large research university, you've got 5 years to bring in $1 million of grants, write at least 10 papers, and then have a few grad students running through the pipe. In addition to teaching, in addition to all the service work that you're expected to do. So hiring committees, undergraduate advising, student organization, management, all that kind of stuff. You're supposed to do all that, and you've got 5 years to prove yourself. Once you got that, if you're able to pass tenure, then you win the big prize. You've got a meal ticket for the rest of your life. You can't be fired. I mean, you can be fired. You can be fired from a professorship position. One, if you don't show up to class to actually teach, you will get fired for that. And two, if there's gross moral turpitude, you can get fired for that too. But generally, you have a job. Now, this job won't pay summer salary. This job won't pay for gear or equipment or lab or students, employees or grad students or postdocs. In order to pay for all that, you need grants. In order to get grants, you have to write more papers and keep your research going. So you can. Once you're tenured, you can totally just shut off, teach a couple classes every semester, serve on some committees. You won't get promoted past associate professor. You won't get any, pay increases, but you'll have a job for the rest of your life. So you can just sit back and relax. By now you're in like your mid 40s, so you got another 20 years of just chilling. But that's it. But if you want anything else, if you want to actually advance any kind of serious research program, you have to get grants. What's an example of gross moral turpitude? That's a great phrase, but that's the exact language that's used in a lot of academic settings. So like, I don't know, sleeping with a student is probably going to be frowned upon, or committing total fraud, academic fraud. So, making up results in your lab and punishing. That's gross moral turpitude. That will get you fired. And there are plenty of examples of professors who for years have faked results, have cheated in their labs, have made up things, and then the truth comes out, and I don't care if you got tenure or not, buddy, you're gone. You're gone. Do I have an opinion on conformal cyclic cosmology? This is one of these ideas where the universe cycles in and out of multiple big bangs. These ideas are always kind of nice and appealing, but they don't have a lot of meaty hooks. And so if there's no meaty hooks, if there's no way to test it, if there's no way to point our telescopes or our observatories, give us some weight. Don't just give me an idea, give me some meat on it, right? Give me some protein. And until then, it's a nice idea. I'm a high school freshman. I really want to pursue a career in astrophysics with a Ph.D. Any tips? And it also was the typical path for an astrophysicist. So if you're a high school freshman, if you really, really want to go down this road of getting a PhD in physics or astronomy or astrophysics, if you really want to aim for that academic position, despite all of my warnings, your first goal is college. There's the big goal. There's the big goal of getting your PhD and searching for position, but it's staged. Don't worry about that end goal yet. Your goal now, as a freshman in high school, is to do a good job in high school. Don't worry so much about the classes you'll take, because honestly, it doesn't matter. Guess what? I didn't take a single physics class in high school. No joke. I didn't take any physics in high school. I took computer science. In fact, I started college as a computer science major and I switched to physics 3 years in. The classes you take in high school don't really matter. They matter for entering into a program. Once you're in college, no one cares what you took in high school. So your job now is to just do good in high school in all your subjects. Maintain a high GPA, do your extracurriculars, write an essay, all that. Just be a good high school student. That will serve you well whether you end up pursuing a career in physics or astronomy or not. Just be a good high school student. Then when you look to colleges, apply to the best colleges you can find. And you'll learn this. You'll get this from your guidance counselors. You're going to apply to a dozen colleges minimum. And based on your GPA, based on your track record, you'll have some idea of where you're going to land in terms of eliteness or prestigiosity. Making up words now, because it's just me alone on the far side of the moon here. You have various levels, and so you'll have a sense. You'll have a rough sense of where you land. So you'll apply to schools there, a few higher up, and a few safety schools below that. You'll blast it out, and you'll get a bunch of rejections and a few acceptances. Then you go visit, see which culture, which campus culture best fits you, and then you go for it. And then your job there is to be a good college student. And then from there, you apply to grad school, but that's 4 years later. So you are at least 7 years away. 7 years away from worrying about grad school and where to apply for grad school. And then you are at least like 13 years away from worrying about what to do after you get your PhD. So just take your time. Focus on being a good high school student, because that will serve you well no matter what. Face Gallon, if you're 37-year-old, can I get a career in this? Oh, for sure. So one route for people who are just getting interested in astronomy and physics and want to get into it, one route is totally to jump in, to take your GRE, get a good score, study up, try again into grad school, do the whole PhD route. There's plenty of I say older people because I'm 36, so it's like if there was someone in grad school who's 37, that's not going to really raise any eyebrows. There are plenty of people to do that, and that's totally cool. Another approach is to take a look at your own skill set and ask, what could you bring to the research table? So I actually know someone who's a very good software developer, who's a very good programmer, and got interested in astronomy and physics, and just started shopping around saying, hey, I've got skills, I'm into this, I speak the lingo, can I get a job? Even though I don't have a PhD, can I get a job? And he ended up he works a lot with LIGO, the Gravitational Wave Observatory, and he's doing great work with LIGO, and he's flying to conferences, and he's giving presentations, and he's writing journal articles without a PhD, but because he took his skill set, he found a need for that skill set, and he plugged himself in. Andrew, that's a good point. I'd like to add that you should be discerning about your college after you enroll. Don't let the initial tuition trap you if you don't feel like you will succeed there. That is for sure. So I switched schools. In college. I was going to Embry-Riddle Aeronautical University in Daytona Beach, Florida. After 2 years, or like a year and a half, I felt like it wasn't really working for me. Even though I had a scholarship there, I was doing well there. I liked my classes and my professors. It just wasn't clicking for me, and so I transferred out to a different school. That made all the difference for me. I found a home there, and I really, really enjoyed it. So don't let your initial school. You can always transfer. You can always switch. And this is true in life, right? Don't ever feel like you are trapped, because you are not. You are never trapped in your current situation. That is true in life. You're never trapped. You can always get out. It's never too late. Even if you're 37 years old. Andrew Cox, high school is not teenage daycare. College. Does this happen to everyone? Because when I first went to college, I'm like, I'm an adult. And now, at the ripe old age of 36, people come into my class, freshmen come into my class, and I'm like, when do they let babies into college? How young are we starting now? Are we skipping like middle school? Seriously, you look like 6th graders. Like, I'm pretty sure you're 12 years old. They look so young. College is daycare. College is daycare for sure. Andrew Cox, academic fraud is a big deal. Hearing from those who peer review committees who verify published rules. Oh yeah, academic fraud is giant. I mean, this is your reputation. Is when you write a journal article representing your work, saying this is me. This is the honest work that I did. These are the results that I got that I am reporting to the community, and the other members of the community are relying on you to tell the truth. You don't have to be right, but you have to tell the truth so that we can say, oh, yeah. See, they did it and they got this result, and I agree or disagree because of this reason. This is how science is done. But if you start faking results, if you start fudging results, if you start fudging numbers, if you start, not doing what you're supposed to, other scientists can't rely on you. They can't cite your work. They can't compare or contrast against your results because your results are garbage. They're meaningless. So academic fraud is huge, tremendously important. And that it does tend to get a lot of people, not a lot of people, but when professors lose their positions, usually it's because of academic fraud, because they got lazy, because they got greedy, because they had a lot of hubris, all the usual reasons why people set themselves up to fail. They did. Hey, Astro B, the topic is whatever I want it to be and whatever people ask. So, sorry, Sam, if you're getting bored, just leave, dude. I'm not holding you here. It's never too late to change. Yeah, and the topic is science. The topic is space. This is an open QA, which is going to be every Sunday night. Well, I'm not going to promise not every Sunday night, but let's get this clear. This is my show. It's my show. And everything I said, oh, hi, Lemony, I'll say hi to you. Everything I said, I'd see some people remarking about US. So I did spend time in Paris and in Italy. I got to see, and I have tons of collaborators and friends who grew up in the European school system and college and postgraduate careers, and also the British one. Of course, there are variations there. College is a different ballgame. There is a different experience. Graduate schools are very, very different in Europe than they are in the US. They tend to be much shorter, only 3 years long instead of like 5 to 7 in the US. I don't want to say they're more like an extended master's program. They're a little bit more focused. They don't involve coursework very much, if at all. But the general advice still applies that, focus on where you are now, the stage you are now, and do a good job at that. Be present in the moment, because the future is hard to predict. The future is difficult to control. You have some things about the future that you can control and many things you can't. So focus on the present, focus on what you are now, and be the best person or be the best student, be the best worker that you can be now, so you maximize the amount of options that you have in the future. And unfortunately, I'm going to call it a wrap for tonight. Because I'm tired. This was just an experiment, but I'm looking to do these every single Sunday at 8 p.m. Eastern. May not hit every Sunday. It depends on my travel schedule and book event schedules. But I hope to drop in, just have this kind of casual conversation with you guys. And I'll see you next week, hopefully.